Are you able to hear me? Okay. So I have not prepared any slides for the today's topics. Just I will explain you about it. It is a continuation of the supervised learning algorithm. So we will be discussing about naive-Bayes classifier algorithm first, and I will take one example through which I will explain to you how it works. So first, uh, what is naive-Bayes classifier algorithm? It's basically a supervised learning algorithm, and it is based on Bayes theorem. So Bayes theorem already I have explained you in earlier class. So I will not go thoroughly into the Bayes theorem. Just hear how Bayes theorem is used or applied in naive-Bayes classifier algorithm that I will discuss. So this algorithm is mainly used in text classification that includes a high dimensional training dataset, and it is one of the most simple and effective classification algorithm which helps in building the fast machine learning models and can make quick predictions. I will explain this algorithm with an example which I will show to you. Just let me share the screen. Are you able to see my screen now? In the right hand side, can you see that note application is showing? Can you confirm anyone?
Yes, sir.
Okay. So here we will be discussing today the ninth base word. So whatever I have written, are you able to see? Just anybody can tell yes or no. What I have now written, are you able to see or not? Hope you are able to see. I'm writing again. Okay. You are able to see it. So in that base how the it is calculating the probability of a particular object and how it was the base of determining. So here it is also used the probability. So it is a probabilistic classifier also. So it comprises of two words. Knife and base. Base here I've already told you that it depends on the base rule or base law or base theorem. So knife means because it assumes the occurrence of a certain feature is independent of the occurrence of the other feature. So suppose a fruit is there and it is classified on the basis of color, shape, then taste, and shape also. So in shape, if it is red, spherical, and it is sweet, then it will be recognized as apple. So each feature is individually contributing to identify that the fruit is an apple without depending upon each other. So every individual feature is considered here to identify an apple. So that's why we call this as name. And base theorem, you already know that it's based upon the base theorem. So the formula was what we have already earlier discussed as E of A B equal P. So its probability. So it is the base theorem where PAB is the probability of hypothesis A on the observed event B, and then P of B is the probability of B upon A is the evidence that the probability of the hypothesis is true, and PA is the probability of hypothesis before observing the evidence, and probability of B is the probability of the evidence. So it will be calculated. With an example, we will see how it will be calculated. Just in the base theorem, I already explained it about with an example. Here also we'll see with the working of knife-based classifier. Suppose one condition is there, weather condition, and our target variable is play. This means in this data set we are considering that whether the weather is deciding the player should play on a particular day according to the weather condition or not. So the problem statement is if the weather is sunny, then the player should play or not. So this we will try to solve actually. First we will construct one table. Here, what we can write first, we'll write rainy, and we can consider that the player can play. So for every weather condition, we are writing yes or no. After that, we will find out for that problem statement whether the weather is sunny, then the player should play or not. That we will have to find. And it will be starting from zero only. And sunny, yes. Overcast, yes. And again on same condition, overcast, yes. So just we are writing this various weather conditions and the playable condition of the player. So that's why it's writing here overcast, yes, and again overcast, yes. So yes, some of the conditions are there, and based upon that we will find. So we can write this here, and we have to only determine. Conditions may be similar also in the table, but based upon that we have to determine. The table will continue. So finally we are having this condition on the data set. So here we have to calculate all the weather conditions. Frequency table we have to prepare from this above table. Whether then yes or no. These are the weather conditions. So how many yes condition is there for overcast? And here we have to calculate. 1, 2, and 3, and 4 and 5. Okay, 5 years conditions for overcast weather condition. Then for rainy, we have to write from here. 1, here was yes. Actually, that's a mistake. So yes, conditions for rainy weather. Then for sunny, yes, will be 1, 2, 3. Then we will again write for no conditions for the weather condition overcast. So similarly, we have to see it from here. Overcast means no overcast condition is there, so we write as 0. Then no rainy weather condition is 1 and 2. Similarly for sunny, no condition. So it will be 2 only. Then total what we'll can write was 5, 10 plus 2, 4. Then from above table we will make another table as likelihood table. The weather condition. From above we can write 0 for overcast, rainy to sunny to, and overcast yes 5, rainy yes 2, sunny yes 3. So from the very first table, how many conditions were there total? 14. Just see here. Just started from 0 till 13. So 14 will be the total conditions. Here we will write no was 0, so directly we can write 5 by 14 equals 0.25. Rainy 2 plus 2 4, and write directly 4 by 14 equal 0.29. And 2 plus 3 for sunny, we can write 5 by 14 equal 0.35. So total here I can write 2 plus 2 4. We also were writing total divided by 14 as 0.29. And here 5 plus 2 plus 3 10 divided by 14 as 0.71. Like this we are getting like table outcomes. So we will apply the base theorem here. So we are applying the base theorem for yes, probability of yes and weather conditions sunny will be what? Probability of yes to probability of yes all divided by probability of sunny. Now we will calculate what is the probability of sunny yes condition. From the above we can see 3. Probability of sunny yes is 3. Out of 10. So total yes conditions was 10. Here also we are writing 10. Here from here we can see it was 10. Yes condition. Then we will get this 0.3. So for probability sunny, because directly from here we can write 0.35. From this you can see total you are writing 2 plus 3, 5 divided by 14. So it will be the probability of Sunny here, and then probability of total yes will be 0.71. You can see it from here. This was the probability of yes 10 divided by 14 is 0.71. So we are writing this here. Then we are putting these values into the base theory here. Finally, we are getting this value. But we have to check for the no condition also, so that we can tell that based upon the probability which is larger. So if Sunny is yes, then the player will play, and if there is no sun, then it will not play. So like that, we have to calculate for the no condition also. So that we will calculate again. From the above tables only, we will get these values. Similarly, like the Sunny and yes. So for Sunny, it is 2 and the total no was 4. And for probability of no, just calculated 0.29 here. So we add this, and then probability of Sunny. From here only we can write here also. And finally, we are putting all these values in this formula. So calculating all this, we will get like this 0.41. So what we can conclude from these two values 0.41 and 0.6, probability of yes sunny is greater than probability of no sun. So from this only we will conclude that on sunny day player can play the game. Hope you are able to understand this, how naive-Bayes theorem is used for a particular condition in a problem statement. Any doubt till now? Okay, so some of the advantages of naive-Bayes classifier is it is one of the fast and easy machine learning algorithm to predict a class of datasets, and it can be used for binary as well as multi-class classifications. So it was in the earlier example only we have seen that it is used for the multi-class classifications, and it is also used for text classification problems. So these are some of the advantages of using naive-Bayes classifier algorithm. Then the disadvantage of it is that it assumes all the features are independent or unrelated, and it cannot learn the relationship between the features. So from the earlier example only, we have seen that it was considered as the independent features for that particular problem statement, and the relationship cannot be established from those features. So this will be the advantage of naive-Bayes classifier algorithm. And some of the applications of using the naive-Bayes classifier algorithm is it is used for credit scoring. So in banking system, if you know that whenever we apply for a loan, then there is one parameter which the banks check that is called the CIBIL score. So each individual has a kind of CIBIL score uh, which will tell whether he is or she is able to get the loan or not. So that it is used for calculation. Then also it is used in medical data classification, and also it is used in real-time predictions. Already I have told you it is used in text classification such as spam filtering and sentiment analysis. So some of the things we will see in later class also, whatever I have explained you about the applications, this we will see After that, moving on to the next, we will be looking at GBM, which is gradient boosting machine, and it is also one of the popular technology used to build predictive models for various complex regression and classification tasks. So it is your gradient boosting machine or GBM. Now, as we have came to know about the GBM, so this boosting algorithm, so it follows the concept of ensemble learning, where it combines multiple simple models with learners or base estimators to generate the final output. How we can use this algorithm through coding in Python, we will see later on. Just for to give you the idea what are these algorithms, I have explained you about it. Later on, we will see how we can apply in a real data set and how we can develop model that we will see later on. It will give you the final output. So it first starts with building a primary model from available training data. Then identify the errors. Present in the model. Yes. After identifying this, after identifying the errors in the base model, and secondary model is built. After that, again identifying, third model is built. It will continue till we it will continue till the training data set is complete and the model is corrected correctly predicted. This we will see with an simple example. Suppose we have three different models, each working completely differently. One is your linear regression model, which will show linear relationship in the data. Then one is your decision tree model, which will try to capture the non-linearity in data. And likewise, one more model we can consider SVM. Suppose we are considering support vector machine. So all these models will be used for the final prediction. It's combined. This also we can take the average of each model instead of using the individual models prediction. Average we can consider of all those three models. So finally, we will be getting this the performance of the model based upon the information from all those individual models and averaging the predictions of the models. So mainly four boosting algorithms are there in machine learning. So one is your GBM that I've already told you, and XGBM, then one is GBM and CAD Boost, Extreme Gradient in GBM. So before moving on to this four algorithms, we'll see how most of the models are used in GBM. So through in simple technique only, it will be depending on the combination of various models together, and we can say that multiple base models contribute to the predictions, and average of all predictions uh, is taken by the boosting algorithms. And I have told you about the strong classifier and the weak classifier here. So it is mainly dependent upon the strong classifier is mainly dependent upon the high accuracy, and it performs well, and it can make decisions with high confidence, and also it is capable of correctly classifying most of the data points in a data set, and the accuracy is mostly greater than 80%, so that we can tell it as strong classifier. And the weak classifier is the model that performs slightly better than random guessing, but the accuracy is very low, and the error rate is around 50%, is greater than 50% actually, but less than 100%. So based upon that, we can tell about the performance of the particular model. And here also I've told you about weak learners. So weak learner are the base models that learn from the past errors, and they are helping to build a strong predictive model for boosting algorithms in machine learning. So that I have already told you. So certain models are there. So based upon that, we are predicting for a strong model and eliminating the errors from those models, we will get a final model. So generally, decision trees work as weak learners in boosting algorithms. So how we can train the weak learners? So first of all, we have training data set where we can train the base learners, and based on the prediction from the previous learner, it improves its performance, and it will be focusing on the rows of the training data where the previous tree had the largest errors. For example, the shallow trees are considered weak learner to decision trees as it contains few splits. So generally in boosting algorithms, trees having 6 splits most commonly. So this splitting also we can get the better idea with example which we will be discussing in next classes. Then you can get the better idea. So for now, just I'm giving you the brief about it. Suppose we are having a data set and we fit a decision tree into it. And we are writing it as f of x y equal y. Then we are fitting the next decision tree with largest errors of previous tree, which will be denoting as each of 1 x equal y. Just take, read it as it is. It is denoted in mathematical notations. So in if we are applying it really, then it will be based upon the libraries which we will be using. So directly from that we are importing, and in program like that we will generate, and we will be getting the model. So this might be quite uh, typical for you, these mathematical notations. I'm just explaining it to you. Then we will be adding this new tree to algorithm by adding step 1 and step 2. We will get it as f2x equal f1x plus h1x. Again, we will fit the next decision tree with the residuals of the previous tree. So we will be getting it like this. As h2x f2x. Again, we will repeat it in the third step. Similarly, we will repeat f of 3x f3x. We will be getting like this. We combine above, and this process will continue until the certain mechanisms stop it, and this is called a cross validation. So the final model will be a stage-wise additive model of b individual trees, as we can write it as b of summation of b equal 1 f b x. So best split points will be chosen, and the loss will be minimized by this. So this will be through programming we achieve it, and we are just splitting one by one. So as told you about six splits. So basically we will be taking six splits and then one after one we will be adding, and finally we will be getting the best outcome of the model. Then comes the extreme gradient boosting, XGBM. So it basically a latest version of gradient boosting machine, uh, which works just like GPM. So here the trees are added sequentially, one at a time, and that learn from the errors of previous tree and improve them. They might look similar, but there are still some differences between XGBM and GBM. So XGBM uses various regularization technique to reduce underfitting and overfitting of the model, which also increases model performance more than gradient boosting machines. So underfitting and overfitting, I have just explained you sometimes earlier. In earlier class, I have explained you. So that we are when comparing one model. So here we are getting this uh, data points below here. So this will be underfitting, and the overfitting will be it will be above it, and best fitting will be lying somewhere near it or in this straight line only. So XBGM also we can use in gradient boosting in boosting algorithms, and then comes the light GBM, LGBM. So it is an upgraded version of gradient boosting machine, as it is efficient and faster in speed. So unlike GBM and XGBM, it can handle huge amount of data without any complexity. And as it is suitable for huge amount of data, it is not suitable for data points which are very less in number. So instead of level wise, it prefers leaf wise growth of the nodes of the tree. Suppose we have this tree. So these are two leaf nodes. So it will LGBM will directly split it into two secondary nodes, and later it chooses one secondary node to split, and it will split this leaf node. Again, it will be splitted further, and it will be splitted until we get the particular best performance out of it. That's why it is preferred over others where large amount of data is there. Then comes the cat boost. So it is used mainly to handle the categorical features. I have already told you about the case of Apple, so that some categorical features are there. So that is also can be handled by the cat boost algorithm. It is mainly used to handle the categorical variables into numeric data. So in the categorical features, we can use it to convert it into numerical data. One more algorithm will be there in boosting algorithms. So ADA boost, we will discuss it in the next class. So till now, any doubt you have, you can ask. After this class, you just go through all the algorithms I have discussed today. You will get the better idea how it can be, how these all algorithms are different, and how in different cases we can use them. And also after the explaining these algorithms, we will be able to see it in the uh, real data sets. Then it will give better idea to you. Any doubt till now? Can ask any questions.